Okay, before we get to actually calculating the electrostatic force between different objects, what I'd like to do is talk very briefly about the graphs that we can make with this. Again, remember, the equation for electrostatic force, otherwise known as Coulomb's law, is K Q1 Q2 over R squared, and that's equal to Fe, Fe being the electrostatic force, K being the electrostatic constant, given on the reference tables. Q1 and Q2 are magnitudes of charges. R is the distance between the centers of each charge. If we were to graph Fe versus Q, take a look at either of these Q's, okay? There's no squareds on them or anything. They're in the top of the equation. Imagine if I were to double Q1, that would make this entire side double, which means Fe would double. If I were to triple, let's say Q1, the same thing. This would triple. That points to a linear relationship. So the relationship between Fe and Q should be a straight line relationship. This again is known as linear. The relationship between Fe and R, on the other hand, is a little more complicated. First of all, that R is in the denominator. That means that if R increases, this entire side decreases, so Fe goes down. That type of relationship is called an inverse relationship. If one thing goes up, the other goes down, okay? And it's squared. So not only do we have an inverse relationship, we have what is known as an inverse squared relationship. Inverse square, okay? So if you're asked a graph about asked a question about either of these graphs, you should know the shape, okay? And this is similar to what we've been doing all year in terms of graph shapes. So let's get to some calculations. In a hydrogen atom, the orbiting electron is about 5 times 10 to the negative 11th meters from the proton, which is in the nucleus. What is the electrostatic force between the electron and the proton? So essentially what we're looking for here is what's the force between the electron and the proton in a hydrogen atom, the most simple type of atom where there is one proton, one electron. Well, our equation is Fe equals K Q1 Q2 over R squared. K, if you remember from the reference tables, is, 8.99 times 10 to the 9th newtons times meters squared over coulomb squared. So I'm going to write that all out. 8.99 times 10 to the 9th newtons times meters squared over coulomb squared. And now we need the charges. Well, it doesn't even tell us charges. Okay, it doesn't say any numbers about the charge, but it does tell us what particles we're dealing with here, an electron and a proton. And the thing about electron and proton is there's tons and tons of differences, but the charges of the electron and proton are very similar. The only difference is that one is positive, the proton, the other is negative, the electron. The amount of charge is exactly the same, 1 elementary charge. But we need that in coulombs. 1 elementary charge, in other words, the charge of both an electron and a proton, the only difference is the sign, is 1.6 times 10 to the negative 19th C. So 1.6 times 10 to the negative 19th C. There's for the proton. And for the electron, remember, I'm not going to put in that negative. You don't want to put negatives into this equation and confuse yourself when you get a negative answer. All I'm going to do is I'm going to remember that this electron is negative, this proton is positive. Okay, I'm just going to mark that down out there. So the magnitude of the charge is the same for both, and it tells us that the electron is 5 times 10 to the negative 11th meters away from the proton. The physics is done. Now all I have to do is some math. And you do have to be careful with the math. This is another time where you need to know how to use scientific notation, okay? And you need to know how that works on your calculator. What I'm going to do is I'm going to do this in steps, I think. I'm going to do 8.99 e to the 9th times 1.6 e to the negative 19th times 1.6 e to the negative 19th. And what I get on the top is 2.30144 times 10 to the negative 28th. Now, I want to divide this by the bottom. So you know what? I'll just write this out here. And I'll show you multiple ways that you can do stuff like this. Okay, times 10 to the negative 28th. All right, on the bottom, we have 5e negative 11 times, since it's squared, 5e negative 11. That gives us 2.5 times 10 to the 21st. So an easy strategy is figure out the top, write it off to the side, figure out the bottom, write it off to the side, divide the two of them. 2.30144 e negative 28 divided by 2.5 e negative 21. And what we end up with is 0.000000092. I'm going to put that into scientific notation. How many times do you have to move the decimal before we get all the way to across the 9? 1, 2, 3, 4, 5, 6, 7, 8. So this must be 9.2 times 10 to the negative 8. And the units of electrostatic force are newtons. Now, why did I write down that one's negative, one's positive up here? I'm not going to change the sign of this at all. All that is to do is to tell us whether this is attractive or repulsive. Are the electron and the proton attracted to each other, or are they repelled by each other? The answer, obviously, is they're attracted to one another. So I'm just going to write down that this force is attractive. So is that the force that holds an atom together? Well, it might have something to do with it. What other force tends to hold things together? Well, what about gravity? Isn't there going to be a force of gravity between the electron and the proton? Absolutely. Let's find out how big it is. Fg equals, remember, G m1 m2 over r squared. G is on the front of the reference tables. First one up here, universal gravitational constant, 6.67 times 10 to the negative 11th. And the units, newtons times meters squared over kilograms squared. Now what about the masses? It doesn't tell us the masses. Well, it tells us what the objects are. Again, rest mass of an electron, rest mass of a proton. Very, very small, if you notice. Rest mass of an electron, 9.11. And don't worry about that word rest. Maybe we'll talk about that towards the end of the year. 9.11 times 10 to the negative 31st, and 1.67 times 10 to the 27th kilograms. Divided by, well, the same distance. 5 times 10 to the negative 11th meters, and that gets squared. I'm going to show you what you'd have to do if you want to type all this in at once, at least on this type of calculator. 6.67 e negative 11 times 9.11 e negative 31st times 1.67 e negative 27th. Okay, that's all well and good. Now what I'm going to do is I'm going to divide. I'm going to open up a parenthesis. 5e negative 11. I'm going to square that, close the parenthesis, divide. And it almost looks like that should be the wrong answer. I'm going to round this to 2 decimal places. 4.06 times 10 to the, look at that, negative 47th newtons. It looks like it's a mistake. Guess what? It's not. This doesn't mean that the force of gravity is approximately 40 times smaller than the electrostatic force. That's not what this means. What this shows right here is that the force of gravity is like a 1 and then, well, no, here, let me go the other way. The electrostatic force is somewhere approximately about 10 to the 40th times bigger than Fg. It's 1 times, that's a 1 followed by approximately 40 zeros times bigger. The force of gravity is not even significant in holding the atom together, okay? The gravitational attraction between the electron and the proton is tiny compared to the electrostatic attraction between the electron and the proton. So gravity really doesn't have much to do with holding an atom together. Atoms are held together, at least this part of the atom. The electrons are bound to bound to the protons by in part the electrostatic force, the force between them. Now obviously it's more complicated than that, but this is the reason they stay together. Okay, Fe is nearly 1 followed by 40 zeros times stronger in this situation. And the real reason for that, if you look at the equation, the distances are the same, the masses are smaller numbers than the charges, and the gravitational constant is much smaller than the electrostatic constant. The electrostatic constant is actually a huge number. It's like 9 billion, approximately. All right, a couple more examples with the electrostatic force, and we'll call it a day. Two charges are placed in a row as shown below. What is the electrostatic force between charge 1 and charge 2? Charge 1 has a charge of positive 1e. Charge 2 has a charge of positive 2e. Now remember, we can't use this equation unless these are in coulombs. So real quick right now, I'm going to write this down. Very quick, 1e, we already know that. That's 1.6 times 10 to the negative 19th coulombs. 2e plus 2e, well, come on, let's be obvious. What's twice this? Okay, you just double this number. 3.2 times 10 to the negative 19th. Okay? Very quick. Fe equals k q1 q2 over r squared. 8.99 times 10 to the 9th newtons times meters squared over coulomb squared. 1.6 times 10 to the negative 19th c. 3.2 times 10 to the negative 19th c. How far apart are they? 8 times 10 to the negative 9th meters, and that has to get squared. By the way, remember the force of gravity is attractive. I forgot to write that down before, but it doesn't play any noticeable role in holding the atom together. So, how big is the electrostatic force in this case? Try it yourself. I'm going to do it at the same time. Okay, so I'm going to show you something different. Now this is the top that I've got. I'm going to divide it by 8 times 10 to the 9th once, and then I'm going to do it again because that's what squared means. This part happens twice, 8 times 10 to the negative 9th times 8 times 10 to the negative 9th, but in this case we're just going to divide by it twice. So the electrostatic force between them in this situation is 7.192 times 10 to the negative 12 newtons. By the way, notice this is an extremely, extremely small force. We're dealing with small forces here because we're not dealing with large amounts of charge. Okay, this would not be noticeable to you, but to something the size of this, it's it's a pretty big force. Okay, it can cause big accelerations. So here's the electrostatic force in this situation. Now I'm going to show you an algebraic method for solving questions. If charge 2 is moved 3 times as far away, what will the new electrostatic force be? I could very easily, just off to the side, take this number, 8 times 10 to the 9th, multiply it by 3, plug it right back into the same equation, okay? And then, square the new radius times 3. This is going to be the same. I'd get my new answer. I don't want to do it that way, though. I want to do it the algebraic way. Either there's a bigger chance of me, messing up the numbers here with my calculator, or it just it takes a while. Once you get used to doing this, it's much easier. The new distance between the charges, I'm going to call r prime. What's the comparison to the original r? Well, if it's 3 times as far away, r prime is equal to 3 times r. So that means Fe prime must be equal to k q1 q2 over r prime squared. R prime was 3 squared. What that means is that Fe prime is equal to k q1 q2 over 3r, whole thing squared. Now, I want to get rid of that parentheses. If I take 3r and multiply by itself, 3r times 3r is going to give me 9r squared. And once again, as I've done in the past, look what I have here. K q1 q2 over r squared. Isn't that just what I had as Fe in the first place, excluding this 9? That 9 is on the bottom. So I realize that this new force should just be 1/9, or Fe over 9, the size it was originally. I already have the force, the original force, 7.192 times 10 to the negative 12. Divide that by 9. And I end up with 7.99 times 10 to the negative 13th newtons is the new force. Okay? Once you get used to this method, much quicker, much more powerful. If you don't believe me that the other method would have worked, watch this. 8e negative 9, multiply that by 3. I get, let's see, can I convert this to scientific notation easily on this calculator? There's definitely a way to do it. Okay, 2.4 times 10 to the 8th. Great. So 2.4 times 10 to the 8th, I'm going to go back to floating. 8.99 e, oops, not negative, 9 times 1.6 e 19 times 3.2 e negative 19 divided by, parentheses, 2.4 e negative 8 squared, and parentheses, close it, I get the same thing. Okay? That should be enough to do your homework. I'll explain what that is in a little bit. Let me know if you have any questions. I'll see you guys later.